Hey, this is Brock Lemire's, and we are continuing our study of embedded systems design. And now we're going to start looking at a different class of instructions called the program flow instructions. So up until this point, we've looked at data movement instructions, data manipulation instructions, and now we're getting to our last class of instructions that actually manipulates the flow. So in this video, I just want to give an overview of what these instructions do and talk about what is provided within the MSP430 instruction set. Okay, your program is going to be assembled into opcodes and operands that are going to be put into program memory. Okay, program memory happens to start at address 8000 within the MSP that we're using. And when you begin executing code, the program counter is going to hold the address of the next instruction to go get. So when you reset your computer, program counter is going to be initialized with 8000. And it is going to then, as you start doing your fetch, the fetch operation in the control unit consists of taking this program counter, putting it out on the memory address bus, and reading that first opcode out of the first instruction in program memory, bringing it into the CPU, and decoding it and determining what to do next. What to do next might involve going back and grabbing an operand. If the instruction didn't have an operand, it might involve moving the program counter to the next location in memory. But this fetch, decode, execute cycle, the first two steps involve using this program counter to go out into program memory and grabbing the opcode to know what instruction is going to be executed. The program counter, very important to think about what that is. Okay, now let's look at specifically what we're doing. 8000 is where we are living. That's where our program is going to be downloaded. And under normal operation, you can think of it as, let's say you wrote a program and it consisted of moves and data manipulation instructions, the instructions we've looked at so far. Those are going to be assembled into opcodes and operands, and they're going to be packed in order in program memory. And the program memory is going to start at 8000 and it is going to march down. Okay, it's going to know how many words of memory each instruction takes based upon the opcode. So it will know whether it's going to increment by 1, increment by 2, if it's going to need to read 2 addresses worth of operand, and it's just going to march. And it's just the program counter is marching sequentially through memory. And it's just like next opcode, next operand, next opcode, next operand, next opcode, next operand, next opcode, next operand. And that's how the program execution works. You could immediately see that if you didn't have any instructions or any ability to alter the program counter beyond its sequential execution, you will eventually just march all the way outside of your memory range. Okay, so it will ultimately get into regions of program memory where you don't even have instructions, and worse yet, it might wrap around and start going up here. And as soon as you get outside of the range where your program exists, the computer doesn't know what it's getting. So it's going to go out and it's going to read some piece of information from memory and go, I don't even recognize this as an opcode. And it'll probably just halt and say a legal opcode. So we need ways to alter the program counter beyond its normal sequential mode of operating. Okay. All right, so let's think about this. We're marching along, marching along, marching along, marching along. We're just going 8000, 8002, 8004, 8007, 8008, and it's just marching, marching, marching. If we had an instruction that could then say, let's take the program counter from this value right here and set it back to a previous value, we could create a looping structure. So if we had that ability, we could put this in a mode where we're moving information in from, let's say, a port, we're adding it to something to it, and we're outputting it, and then we repeat. And we can loop, and we can loop, and we can loop. And now we have the ability to actually have a program that runs continuously. We've kind of seen this when we put our main and jump main in there. Now we're finally actually looking at what that instruction does. So the first thing that we need to do is we need the ability to loop. And that will give us the ability to do things like while and for loops that we will program in C. Okay. Just want to highlight one more time. When the program counter is marching along sequentially, that is normal program operation. It gets the opcode, increments, gets the operand if necessary, increments. That is automatic. But we have to specifically put instructions in here if we ever want to change that program counter to a value that is not the next address of the next instruction in memory. Okay, so we know that a looping structure is going to basically be something that alters the program counter up to a previous address. Think about this though. What if we're marching along and all of a sudden we come to a block of code and we did some calculation and we realized that, you know what, I don't want to execute the next set of instructions. What I might want to do is move the program counter down and execute some instructions down here. That is selective execution of code, and that is what gives us the ability to implement things like if, else, and case structures. So for example, when you do an if, else statement in C, you're going to provide code or statements that are executed if the if portion is true. You will provide other statements that are executed if the else portion is true. The way that that's implemented in a computer is the opcodes and operands for the if part and the else part are put into memory. They absolutely exist. Which of those you execute depends on some status that is calculated right before you get to that section of memory, and then you jump over a portion that you don't want to execute. So if the if part wasn't true, we would just hop over it and go execute the else part. Or if the if part was true, we would execute it and then hop over the else part. A case statement could have potentially, let's say you had 16 cases, you would have the opcodes and operands for all of those cases in program memory, and then you would do these selective executions where you hop down here, execute, and then hop over, okay? So we need instructions to be able to execute, or to be able to explicitly alter the program counter. And that is this whole notion of jumps and branches. Those are the names of these instructions, but this is all under the class of program flow. So normal program flow is increment, 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 but then we might need to selectively execute, we might need to loop, and all together you start seeing how a program can become more intelligent and execute code based upon inputs that are dynamic and not fixed when you download your binaries, okay? Okay, now, jumps and branches. These are instructions that set the program counter to different values other than the next subsequent instruction in memory. And like I say, that's how you get your jump, your if else and loops. You have different types of jumps and branches. The first couple are unconditional. Now what this means is that when you get to these instructions, these unconditional jumps and branches, that means it's not looking at a condition. It's simply going to alter the program counter no matter what. The classic example of that is our main jump main. So we get in an infinite loop and we will execute forever. Infinite loops sound bad, except when you try to make a program execute forever. You need a way to continually execute. So unconditional jumps and branches, they're just going to alter the program counter. But conditional instructions will alter the program counter based upon conditions. Now you say, well, what kind of conditions exist? The only thing in the computer that's tracking conditions are the status flags in the status register. So conditional jumps and branches, they look at the V, N, Z, and C flags in the status register and will either jump or not jump based upon these values. Okay? All right. Now, here's the big one. Once you get into program flow, address labels are essential. There's no possible way that you can keep track of all these addresses in their absolute form, so you don't even try. You are going to use address labels like crazy in order to keep track of where you're jumping over, where you're jumping back to. Okay, here is the MSP430 instruction set for program flow instructions, or this is the table that I plucked out all the ones, and I classify these in here. There's some other ones, like I put no-op in here for some reason. It didn't go anywhere else, but the MSP430 provides two unconditional jumps and branches, or two unconditional instructions, and the first one is jump, and its description is jump always. The next one is called branch, and that means branch always, okay? So it's always going to branch. You also have conditional instructions, and you can look at these. So you can have one jump to a label if Z is equal to 1. Okay, that class of that is a conditional jump. Here's its dual, jump to a label of z is equal to 0. Interesting. So I can actually make decisions based on whether the result was a 0 or not. That's kind of handy. I can have jumps that are based upon whether you had a carry or not. You can have jumps that are based upon whether the number was negative, or if it's greater than or equal to 0, or less than equal or less than 0. So you can have all these different conditional jumps, and that starts to give you a sophisticated approach to programming. Okay, now you got to say, what is the difference between a branch and a jump? So the branch is the simplest. A branch is unconditional, and all it does is it moves the value of the source operand into the program counter. So you need a full-blown 16-bit operand, and whatever it is, you just stuff it in there. The good part about that is that you can access the entire 64K address range of the MSP430. Not that you'd want to, though. You really only want you only want to be executing code in the program memory. But it does give you the ability to hit any address within the program memory space. The instruction for it is BR. Okay, and whenever you use this, you almost always use immediate mode addressing to provide the address. So whatever the label is, put a pound sign in before it, and you're off and running. This branch instruction actually takes 3 words of program memory, so it's the most time-consuming instruction. It is actually an emulated instruction. If you come back here, all this does, this is basically a move instruction. If you look at the opcode that is actually implemented for the branch, it's simply a move instruction, and you use immediate addressing. So it's pretty simple, but it also does take a little bit more memory. In order to get an instruction that is smaller, they created this class of instruction called this type of instruction called a jump. Now, what a jump is instead of having a full address that you put into the program counter, what it does is it applies an offset to the program counter. And the offset can be anywhere from -511 up to +512. And so it's a certain number of bits that allow the operand to be smaller. The limit of this is that you're going to take this number and add it to the program counter. And so you can go up in memory with a negative offset, or down in memory with a positive offset. And it makes it smaller, but there's a limit to how far you can move the program counter. These work extremely well for conditions like if, else, in case, where your opcodes and operands are packed tightly together and you're just jumping around addresses that are close to each other. Once you get way down and you have to jump over 30K worth of addresses to get back to the beginning of your program, you might not be able to get a jump. And in fact, if you put a offset in here, you don't have to put the offset. You put an address and it calculates the offset. You put an address label and it calculates it. If you're trying to move too far from where the current program counter is, it'll actually give you an error and say jump out of range. Okay, so if you ever get that, then you have to go to a branch. Okay, all right, we've seen the jump, right? The jump instruction, we've put this in every instruction. We have an unconditional jump, JMP, but that's the difference between a branch and a jump. Okay, so that's the overview of branches and jumps, and next we'll get started with actually doing some examples. As always, subscribe to my channel to stay up to date on all the late videos. See ya.